Let's take a look at this problem from the 2023 Putnam, and it's number A2. Let n be an even positive integer, and suppose p of x is a monic polynomial, that means its leading coefficient is 1, and it's a real polynomial with degree 2n. And suppose we know the following. We know the values of p at positive integers from 1 to n, and negative integers from -1 to -n. And in fact, p of k is 1 over k squared for all of these values. So we see that here, p of 1 is 1 over 1 squared, p of 2 is 1 over 2 squared, etc. And then p of negative k, for k between -1 and -n, is also 1 over k squared. And this here should be a positive. The question asks, for what other real numbers x is p of x equal to 1 over x squared? Now, just looking at the pattern, you might think intuitively that is p of n plus 1 and p of negative the quantity of n plus 1 that are both 1 over n plus 1 squared, but it turns out to be quite different. But we can use a really cool idea to figure out what other values of x satisfy this last equation right over here. So here's a synopsis of what we know. P of k is 1 over k squared for these values of k right over here. Now what we'll do is construct a new polynomial q of x, which multiplies p of x by x squared and then subtracts 1. Why would we do something like that? Well, roots of this equation are precisely solutions to the thing that we wanted. If we have a value of x for which q of x is 0, then this quantity is 0, which means p of x is 1 over x squared. Also, we actually know a bunch of values for which p of x is 1 over x squared, precisely all these 2n values right over here. And so all of these 2n values are then going to be roots of the polynomial q of x. So we know a lot of the factors of q of x, and we can proceed to attempt to find all the other roots, which would then find the other values of x for which p of x is 1 over x squared. Now, it was given in the problem that p of x itself has degree 2n, so that means the degree of q of x is 2 plus that, which is 2n plus 2. And as we mentioned, we actually know n of the roots of this degree 2n plus 2 polynomial. There are these values right over here. And since q of x is monic, again meaning that its leading coefficient is 1, we then know a bunch of the factors of q of x. They're all of these factors right over here, because all of the numbers 1 through n and -1 through -n are roots of q. So the remaining roots of q, which are then the solutions to the equation we're curious about, are the roots of the remaining part of the polynomial right over here, which we'll call s of x. And s of x is going to be quadratic because we have the degree 2n part right over here, and the degree of q is 2n plus 2. So again, since q has degree 2n plus 2, and we know 2n of the roots, there are precisely 2 roots missing for q, which will then give us the solutions to p of x equals 1 over x squared. So let's call those roots r and s and try to figure out what they are. Now, the first observation we can make is that since we're multiplying p of x by x squared, this quantity right over here does not have a constant term. So the constant term of q is actually exactly -1. But the constant term of a polynomial is the product of its roots up to a possible negative sign. And since the degree of q of x is even, is 2n plus 2, the product of the roots is actually going to be precisely -1. The missing roots are r and s, and we know all the other 2n roots, they're right here. So the product of these has to be -1. Now the thing to notice is we were given that n is an even integer, so the number of negative signs that we see here in this part of the product is actually even. And so they all cancel out, and so we get r times s times n factorial times another copy of n factorial is -1. And so r times s is -1 divided by the quantity n factorial squared. Okay, we're making progress to figuring out what r and s are. We know the product. Can we figure out something else? Well, in fact, we can figure out the sum of the roots as well. The key observation here is because we're multiplying x squared by p of x, we actually know that this part of q of x has no x term in it. And so altogether, the coefficient of x in q of x is 0. But there's a way to express the coefficient of x in a polynomial in terms of its roots. And a concise way to write that expression for the coefficient, which is not typically the way that's written when you see it in a lot of videos or literature, is that it's the product of all of the roots times the sum of all the reciprocals of the roots. The reason for this is if you take a reciprocal of a root and multiply by the product, you'll get the product of all the roots except for that one root. And the typical way to represent the coefficient of x in a polynomial in terms of the roots is as the sum of the products of all roots where you take one of the roots out each time. So now the nice thing about this expression is if we add up all of the reciprocals of these roots and the reciprocals of these ones, they actually cancel out. So the thing we're left with is this entire expression on the left multiplied by 1 over r times 1 over s being 0 because the coefficient of x is 0 in q of x. But then that actually implies that 1 over r plus 1 over s is 0 because this quantity that we're multiplying with is non-zero itself. Now if we clear denominators, we'll get r plus s over rs is 0, which implies r plus s is 0. So these two equations together are going to give us exactly what the missing roots r and s are, which will then give us the remaining values of x that satisfy this equation right over here. So rewriting what we have r times s is negative 1 over n factorial squared, and r plus s is 0, which means r is negative s. So we put that together, and we can see pretty quickly that r and s are 1 over n factorial and negative 1 over n factorial, and we can choose which one is r and which is s, it doesn't matter. And so these are the two values that remain for which p of x is 1 over x squared.